international educator.
Hello learner, my name is Ted Owiti, and once again a warm welcome to another Form 2 physics lesson. And today we are going to be talking about Hooke's law, and we'll specifically be talking about the spring constant. And we will also be talking about Hooke's law, what actually stating it, and proving or verifying what it is. So our lesson objectives are: 1, to define what spring constant is, and 2, apply Hooke's law. Okay, so what is a spring constant? Now, the spring constant arises from the relationship between the stretching of a force, stretching force, and the extension of a spring. And Hooke's law basically states that provided the elastic limit is not exceeded, the extension of a spring or of any material is directly proportional to the stretching force. So in short, what we are saying here is that when the force changes by equal amounts, then the extension also changes by equal amounts. If a force changed from 1 Newton to 2 Newtons, all right, that is a change of 1 Newton, all right, and the extension was from 0 to 1, all right, then when the force changes from 2 to 3, then the extension will change from 1 to 2. So basically, equal changes in the forces will produce equal changes in the extension, and that is what Hooke's law states. But it also goes further than that. There is a certain amount of force that you can put on any material that is going to deform it permanently, or it is going to be stretched permanently, all right? So that our equal forces do not produce equal extensions. At this point we know it as the elastic limit, all right? So after the elastic limit, Hooke's law does not apply, because equal forces do not produce equal extensions. So now, for a material that is obeying Hooke's law, then when we plot a graph of the stretching force F against the extension, then obviously when there is no force being applied, the spring will not extend, for starters, right? And as we keep on increasing the force, then the spring will also continue extend. The extension of the spring is also going to continue. So a graph of force against extension must pass through the origin if the material is obeying Hooke's law. So what does that mean? Mathematically, it means that we can write force is directly proportional to extension. Force is directly proportional to extension. And we can get rid of the proportionality sign so that we have force is equals to KE. Force is equals to KE. Of course, F stands for the force, E is the extension, and K is our spring constant. K is our spring constant. Okay, K is the spring constant, and it is got by getting the gradient of the graph of F against E when the spring is still obeying Hooke's law. So something like this. So the gradient of the line is a constant, and that constant is known as the spring constant, or at times it is referred to as the force constant. So if we want to calculate the spring constant, we simply take change in F, which is the change in F, the distance from the change from the top to the bottom of F, the triangle. Well, that is where we have our change in F. And then we also take change in F, or delta F, over delta E. Delta E is simply the change in the extension, and the change in the extension is simply the amount the extension has changed with. And that gives us the what? That gives us the spring constant. So what is this spring constant? What does it mean? What is its significance? All right. What is it? The spring constant is a measure of the stiffness of a spring. The stiffer a spring, the larger the spring constant, and the steeper the gradient. All right. So if you have a spring that is two springs, and one of them is stiffer than the other, then the one that is stiffer will always have a higher force, a higher spring constant, and the graph will always be steeper than that which is less stiff, and of course it will have less it will be less steep. So a stiffer spring extends less than a less stiffer one when the same stretching force is applied on both. So springs can be combined such that the spring constant may increase or decrease. Springs can be combined such that the spring constant may be increased or decreased. So we want to see how to combine springs. There are some cases whereby we want to combine 2 springs or 3 springs or even more. All right. So there are 2 ways in which you can combine springs. You can combine them in series, and you can also combine them in parallel. All right. So let's start with combining them in series. So when springs are arranged as shown, you can see we have one spring on top of the other. Then they are said to be combined in series. They are said to be combined in series. And our 2 springs have a 1 kilogram mass attached to both. So in this case, the 1 kilogram mass, okay, stretches both the upper spring and the lower spring. Remember, or you can see, not remember, but you can see that the upper spring is holding or is carrying the lower spring, and it is also carrying the 1 kilogram mass. All right. So both of the 2 springs are feeling the weight of the 1 kilogram mass. So the spring constant of this sort of spring is less than the one than that of a single spring. So, and that is what we are going to go through and prove. Okay, so consider a spring that stretches by a value x. when loaded by a 1 kilogram mass. So you have a spring, okay, you can see the diagram. It stretches by a value x when a 1 kilogram mass has been placed on it. So from our K is equals to F over E, from our K is equals to F over E, it is easy for us to calculate the force, the spring constant K, and in this case, we know the force is 10 newtons, or rather, the force is actually 10 newtons, all right, and the extension is x. So K is equals to 10 over x. Now, supposing there were two springs that were arranged in series instead of just having one, like let's say that. All right. So we have the two springs, and we have, as we had mentioned earlier, each of these two springs will stretch by the same amount. Now, this particular example assumes that the two springs are weightless, and that the only weight that is acting on the two springs is the weight due to that 1 kilogram mass. Okay, so if that is the case, then it means that we have each spring extending by the same amount, which means we have double the extension. So our extension here is 2x. All right. So using our formula for the spring constant, then we can say 10 over 2x, because the extension is 2x, and you can see that our constant is 5 over x. So you can see the original value of x when it was only one spring was 10 over x. And now when they are two springs, you can see that the value is 5 over x. The spring has, the two springs have a spring constant with less value than the spring when it is all on its own. So a single spring has double the spring constant of two identical springs in series. All right. Now, to get the spring constant K of n identical springs in series, what do? You will simply take the spring constant of the original spring constant and divide it by the number of springs that you have. So if you have 5 springs and the original spring and the spring constant of each of them, let's say, is 2 newtons per meter, all right, then it means that you will be taking 2 divided by 5, so that the spring constant is less than that of a single spring. So let us look at the next arrangement of springs, or the next combination of springs. The next combination of springs is springs in parallel. So when you are combining springs in parallel, you arrange them side by side the way it is shown, all right? And the spring constant of the combination will give us a value that is greater than that of a single spring. With the series connection, let us do the same thing with the parallel connection. So we start off with our single spring that stretches by x, and we know that the force constant is now 10 over x. If we combine the two, now this is where the interesting thing happens. Now this 1 kilogram mass is actually shared between the two so that each of them carries 0.5. All right? They both carry 0.5 kilograms. Okay? So if they're both carrying 0.5 kilograms, then it means that each of them is going to have half the extension it would have had if it was alone. Okay? So since we know that if it is alone, it extends by x, then obviously if they are two, then they will extend by half of x. So if we plug this in our formula of k is equals to f over e, we find that our k is now 20 over x. Remember, when it was alone, the spring constant was 10 over x. Since they are combined in parallel, now the spring constant is 20 over x, which means that it has actually done what? It has doubled. The spring constant has doubled. Now, going by what we know from the spring balance in series, by now you already have an idea of how to get the spring constant of several more springs that have been combined in parallel. Not just how many? Not just two. And in the single one, I'll give you a hint. In the series connection, what we had was the spring constant becoming less by half. All right, to the ratio of half. Now, in the parallel connection, we have the spring constant increasing by twice the amount. All right. In the original, in the series connection, we said that if to get the combined spring constant, you take the original spring constant and you divide it by the number of springs. All right. So obviously, in this case, if we want to get the combined spring constant of springs in parallel, we will do what? We will multiply the original spring constant with the number of springs that we have. And that is exactly what we are going to do. So to get the spring constant k of n identical springs in parallel, you take the number of springs and you multiply by the original value or the original force constant. So basically, that is what we have for our spring constant. What is a spring constant? The spring constant is simply the gradient of force against extension, and it is a measure of the stiffness of a spring. A stiffer spring is always going to have a value of the spring constant is going to be higher than the one that is less stiff. And then again, if you plot a graph of force against extension, the spring constant of a stiffer spring is going to be much steeper, all right? Obviously, because the gradient is steeper, okay, than that of a less stiff spring. So knowing that, let us go through some of the activities that I had planned for us to go through so that we can see we can go through some of the things that we have already discussed in this lesson. So activity number 1. The following readings were obtained when masses were hung on a certain spring. All right. So these are the readings that were taken when masses were hung on a certain spring. So we start off with the mass. When the mass was 0, the pointer reading was 110. And when the mass was 0.02 kilograms, then the pointer reading was 119. When the pointer reading was when the mass hung was 0.04, then the pointer reading went to 129. And when a mass was 0.06, the pointer reading is 138. And finally, a mass of 0.08 kilograms gives a pointer reading of 148. Okay, so what are we supposed to do? All right, so what we are supposed to do is plot a graph of force in newtons against extension in millimeters, and from the graph find A, the extension by the extension by a mass of 0.03 kilograms. Part B, the force needed to produce an extension of 30 centimeters. And lastly, the spring constant of the spring that was used in that particular experiment. So we have, that's our graph paper, and we will need to change the masses into force, so that when the mass is 0, of course the force is 0, and then we will when the mass is 0.02, then the force is 0.2, and we continue doing this until we get the readings for the force in newtons. And to get the extension, we will always be subtracting the original, the reading, the corresponding reading from the initial reading of the pointer before any masses were added. And with that, you can see we have 0 and 9 and 19 and 28 and 38. So armed with this, we need to now plot the graph. On the y-axis, we are going to have the force. On the x-axis, we are going to have the extension. And we are going to have our axis. Remember, axis is always simple and uniform. So we have 0, 0.2, 0.4, 0.6, and 0.8 on the force side. And on the horizontal axis, we have 0, 10, 20, 30, 40, and 50. So now we will plot the points 0, 0, and then 0.2 and 9, 0.4 and 19, 0.6 and 28, and lastly we'll plot 0.8 and 32. And then we will draw a line of best fit as shown. So that is what we have. All right. So I think now we are ready to answer the following questions. What would be the extension by mass of the by a mass of 0.03 kilograms? Remember, the first thing that you need to do is to change the kilograms into newtons. All right. So that we can use the graph. So that will be 0.03 times 10. So we have a force of 0.3 newtons. And we trace the 0.3 newtons on the axis where we have the force. That should be around the center of 0.2 and 0.4. We will draw a horizontal line to the gradient, or rather to the line, and then we will trace where the extension is, and we find it to be 14 centimeters. Then the next question is the force needed to produce an extension of 30 centimeters. Similarly, we are going to trace where 30 centimeters is on the x-axis, and we are going to trace out that so that we get our answer to be 0.064 newtons. 0.064 newtons. All right. And the spring constant. How do we get the spring constant? Remember, this is the delta F, or change in F over change in E, which will give us 0.064 minus 0 divided by 30 minus 0. So that is the force becomes 0.021 newtons per centimeters. The second activity, a spring loaded with a mass of 500 grams has a total length of 15 centimeters. After unloading, the length of the spring is 8 centimeters. Determine the spring constant and state the necessary assumption made in the calculation above. So to determine the spring constant, we need to get the force, and the force in this case, we need to get it from mass times gravity, which gives us 5 newtons. And we also need to get the extension, and the extension in this case is 15 minus 8, which gives us 7. And then to get the spring constant, we simply divide the force over the extension, and we get the answer, that is 5 over 7. Then we get the answer to be 0.714 newtons. State the necessary assumptions. The necessary assumptions that were taken is that the elastic limit has not been exceeded. So we will go through the activity. We'll go through the task. So as we end the lesson, derive expressions that show identical springs in series are less stiff than one single spring. So with that, we come to the end of our lesson. I hope you enjoyed it. Until next time, thank you for watching, and bye-bye.
National Educator.